Arithmetic means. Definition: the arithmetic mean, often just called the average, is the sum of all observations divided by the number of observations. It tells you the typical value if every observation contributed equally. Formula: x bar equals the sum of xi for I equals 1 to n, divided by n where xi is each data point and n is the total number of points. Computation steps. Step 1. List the data. Write all the numbers you have. Example: sales in dollars thousands for 5 stores 12/15/9/2014. Step 2. Add them. 12 plus 15 plus 9 plus 20 plus 14 equals 70. Step 3. Count the observations. Here n equals 5. Step 4. Divide. X bar equals 70 divided by 5 equals 14. The average sales per store is 14,000. Real-world analogy. Imagine you have a pizza cut into 5 equal slices and each slice represents a store's revenue. The arithmetic mean is like reshaping the pizza so each slice has exactly the same amount of cheese. You spread the total cheese evenly across the 5 slices. Weighted mean. Rationale: sometimes data points are not equally important. For example, a manager may want the average price of products, where high-volume items count more than low-volume items. The weighted mean gives each observation a weight that reflects its importance. Formula: x bar sub w equals the sum from I equals 1 to n of wi xi divided by the sum from I equals 1 to n of wi, where wi is the weight for observation xi. Numerical calculation example: a retailer sells 3 products. Product A, price $30, units sold 100. Product B, price $45, units sold 50. Product C, price $20, units sold 150. Here the price is xi and units sold are the weights wi. Step 1. Compute weighted numerator. 30 times 100 plus 45 times 50 plus 20 times 150 equals 3,000 plus 2,250 plus 3,000 equals 8,250. Step 2. Compute total weight. 100 plus 50 plus 150 equals 300. Step 3. Weighted mean price. X bar sub w equals 8,250 divided by 300 equals 27.5. Analogy: think of a class where each student's test score counts, but the class leader's score counts double because they also mentor others. The weighted mean treats the leader's score as if there were 2 identical students with that score. The medians. The median is the middle value when the data are arranged in ascending or descending order. It splits the data set into 2 equal halves. Odd-numbered sample. If n is odd, the median is the value at position n plus 1 divided by 2. Example: data equals 3, 7, 9, 12, 15, n equals 5. Position equals 5 plus 1 divided by 2 equals 3, so the third value is 9. Median equals 9. Even-numbered sample. If n is even, the median is the average of the 2 middle values. That is, positions n divided by 2 and n divided by 2 plus 1. Example: data equals 4, 8, 11, 13, n equals 4. The middle positions are 2 and 3, which correspond to values 8 and 11. Median equals 8 plus 11 divided by 2, which is 9.5. Interpolation method used when data are grouped, for example, in a frequency table. Identify the cumulative frequency that first exceeds n divided by 2, where n is the total number of observations. Use the formula. Median equals L plus the quantity n divided by 2 minus C f sub b, all divided by f, multiplied by w, where L is the lower bound of the median class. C f sub b is the cumulative frequency before the median class. F is the frequency of the median class and w is the class width. Practical example: suppose a retailer groups daily sales in hundreds of dollars as follows. The sales range 0 to 4 has frequency 3. The sales range 4 to 8 has frequency 5. The sales range 8 to 12 has frequency 2. The total number of observations n equals 10. N divided by 2 equals 5. The cumulative frequencies are 3 for the first class and 8 for the second class, so the median lies in the 4 to 8 class. L equals 4, C f sub b equals 3, f equals 5 and w equals 4. Median equals 4 plus open parenthesis 5 minus 3 close parenthesis divided by 5, all multiplied by 4. which is 4 plus 0.4 times 4, giving 4 plus 1.6, which equals 5.600, that is $560. Analogy, imagine lining up students by height. The median height is the height of the student standing exactly in the middle of the line. Sensitivity to skewness. In a right-skewed distribution, long tail to the right, the arithmetic mean is pulled toward the higher values, while the median stays near the bulk of the data. Example, salaries in a tech firm: $50,000, $55,000, $60,000, $65,000, $200,000. Mean equals $86,000, median equals $60,000. The mean overstates the typical salary because of the one very high executive salary. Outliers. An extreme outlier can dramatically change the mean, but has little effect on the median because the median depends only on the order, not the magnitude. Using the same salary data, if the $200,000 salary were $1 million, the mean jumps to $244,000, while the median remains $60,000. Mean is appropriate when the data are symmetrically distributed and you need a value that uses all information. For example, average cost per unit for budgeting. Median is better for skewed data, ordinal data, or when outliers represent anomalies. For example, median household income is often reported because a few ultra-wealthy families would distort the mean. Business decision impact. Using the mean sales figure to set a sales target may be unrealistic if a few flagship stores inflate the average. A median-based target reflects what a typical store can achieve. Population standard deviation. Goal measure how spread out the entire population is around its true mean mu. Derivations start with variance, the average of squared deviations. Sigma squared equals sum over I equals 1 to n of xi minus mu squared divided by n. Sigma equals the square root of the sum over I equals 1 to n of xi minus mu squared divided by n. Y square, squaring makes all deviations positive and emphasizes larger deviations. Step-by-step calculation. Example, a small factory produces 6 batches with defect counts 2, 4, 3, 5, 2, 4. Step 1, find the population mean mu equals open parenthesis 2 plus 4 plus 3 plus 5 plus 2 plus 4 close parenthesis divided by 6 equals 20 divided by 6 approximately 3.33. Step 2, compute each deviation and square it. 2 minus 3.33 squared equals negative 1.33, squared approximately 1.77. 4 minus 3.33 squared equals 0.67, squared approximately 0.45. 3 minus 3.33 squared equals negative 0.33, squared approximately 0.11. 5 minus 3.33 squared equals 1.67, squared approximately 2.78. 2 minus 3.33 squared equals 1.77, same as first. 4 minus 3.33 squared equals 0.45, same as second. Step 3, sum squared deviations. 1.77 plus 0.45 plus 0.1, 1 plus 2.78 plus 1.77 plus 0.45 equals 7.33. Step 4, divide by n6. 7.33 divided by 6 approximately 1.22. Step 5, square root of 1.22 approximately 1.10. Population standard deviation sigma approximately 1.10 defects. Analogy, think of a group of runners. The mean finishing time is the center of the pack. The standard deviation tells you how tightly the runners stay together. A small SD means they finish close to each other. A large SD means the pack is spread out. Sample standard deviation. When you only have a sample of the whole population, using n in the denominator underestimates the variability. To correct this bias, we divide by n-1, Bessel's correction. S equals the square root of the sum from I equals 1 to n of x sub I minus x bar squared, divided by n-1, where x bar is the sample mean and n is the sample size. Computational procedure shortcut formula. Step 1, compute the sum of xi and the sum of xi squared. Step 2, use s equals the square root of the sum of xi squared minus the square of the sum of xi divided by n, all over n-1, which avoids calculating each deviation separately. Example, a consultant surveys 5 customers about monthly spend in dollars. 120, 150, 130, 160, 140. Then equals 5. The sum of xi equals 700. The sum of xi squared equals 99,000. Plug into shortcut, s equals the square root of 99,000 minus 700 squared divided by 5, all over 4, equals the square root of 1,000 divided by 4, equals the square root of 250, approximately 15.81. Thus the sample standard deviation of monthly spend is about $15.8. Analogy: imagine you taste a soup from 5 different ladles. The average flavor intensity is your mean. The sample standard deviation tells you how much the taste varies from ladle to ladle, taking into account that you only sampled 5 ladles out of the whole pot. Variance-standard deviation relationship. Algebraic connection: variance is the square of the standard deviation. Variance equals sigma squared population. Sample variance equals s squared. Therefore, sigma equals square root of variance and vice versa. Interpretation: variance is measured in squared units. For example, 1,000 squared, which is hard to relate to the original data. Taking the square root brings the measure back to the original unit, making it easier for managers to understand. Business example: a company records weekly revenue in $1,000. Variance equals $9,000 squared. The standard deviation equals square root of 9 equals $3,000. Saying revenue typically deviates $3,000 is far more intuitive than saying variance is $9,000 squared. Why both are reported: variance is useful in statistical modeling. For example, ANOVA regression, because algebraic manipulations are simpler with squared terms. Standard deviation is preferred for reporting and decision-making because it shares the same scale as the data. Application of standard deviation in confidence interval and control limit problems. Confidence intervals CI. Purpose: estimate a population mean mu with a range that likely contains the true value. For a large sample, n greater than or equal to 30, or known population sigma, the 95% confidence interval is x bar plus or minus z sub 0.025 times sigma over square root of n, where z sub 0.025 equals 1.96. If sigma is unknown and n is small, use the t distribution. X bar plus or minus t sub alpha over 2 degrees of freedom times s over square root of n. Example: a marketing manager samples 25 stores and finds average weekly sales x bar equals $50,000 with sample standard deviation s equals $8,000. The 95% confidence interval is 50 plus or minus 2.064 times 8 divided by square root of 25 equals 50 plus or minus 2.064 times 1.6 equals 50 plus or minus 3.30. So the true mean weekly sales likely lie between $46.7 thousand and $53.3 thousand. Control limits: statistical process control. In a control chart, the central line is the process mean x bar. Upper and lower control limits UCL and LCL are set at plus or minus 3 sigma. UCL equals x bar plus 3 sigma, LCL equals x bar minus 3 sigma. If a point falls outside these limits, the process is considered out of control. Example: a production line averages 100 units per hour with sigma equals 5. Upper control limit equals 115, lower control limit equals 85. A sudden observation of 122 units per hour signals a special cause, perhaps a machine speed up, that needs investigation. Analogy: think of a basketball player's shooting percentage as a mean. The standard deviation tells you how wiggly his performance is night to night. A confidence interval is like saying, I am 95% sure his true shooting skill lies between 45% and 55%. Control limits are like a coach's alarm. If the player suddenly shoots 80% in a game, far beyond plus or minus 3 sigma, the coach knows something unusual is happening. MBA exams often combine several of the concepts above in one multi-step problem. A typical format: 1. Data presentation, a table with sales figures, frequencies, or costs. 2. Task: compute the weighted mean. Use revenue weights to find the average price. 3. Task B: find the median. Order the data, handle even or odd size, possibly use interpolation if data are grouped. 4. Task C: calculate sample standard deviation. Apply the shortcut formula, remember n-1. 5. Task D. Build a 95% confidence interval for the mean. Use the mean and sample standard deviation from step C. 6. Task E. Interpret. Explain which measure mean or median better represents the central tendency given the presence of outliers, and comment on whether the process is in control based on the control limit rule. Sample question outline. A retail chain records weekly sales in dollars thousands for 10 stores: 12, 15, 9, 20, 14, 35, 11, 13, 18, 40. A. Compute the arithmetic mean and the median. B. One store 40 is known to be a flagship outlier. Ray. Compute the mean after assigning a weight of 0.5 to that store. C. Determine the sample standard deviation of the original 10 values. D. Provide a 95% confidence interval for the true average weekly sales. E. Based on the results, advise senior management which measure mean or median they should use for budgeting, and whether the sales variation suggests the need for tighter operational controls. The answer requires sorting data for median, even, n average of 5th and 6th values, weighted mean calculation, adjust weight for outlier, sample standard deviation using n-1, confidence interval using T0.0259, interpretation linking skewness, outlier impact, and control limit concepts. Such questions test not only computational skill, but also the ability to interpret statistical output in a business decision context.